Right, today I'm going to be doing a video on the Cauchy condensation principle or method, which basically it looks so random, but it's actually so powerful and it's so easy once you actually understand like what it does and how to get to it. And this is all it's saying. It's saying that if we have a sequence, AK, AK is just a random sequence, it's gonna have the same like behavior as a different sequence, 2 to the power of h, a to h. So this is all it's saying. It's DC sequences, at infinity, they're going to be asymptotically equivalent. So if this guy diverges, this guy also diverges. If this guy converges, then this guy also converges. So but they basically act as the same sequence as k or as h goes to infinity. And all we basically do for the sequence is to replace, the index k with the index 2 to the power of h, and we also multiply every term by 2 to the power of h. That's all we do. And why does this actually make it asymptotically equivalent, and why is it so powerful? For example, the famous harmonic series, the sum of all numbers from n equals 1 to infinity of 1 over n. Well, we know that sum diverges. It diverges to infinity. It's 1 plus 1 half plus 1 third, and this gets smaller and smaller and smaller. But the sum actually goes to infinity, and it's kind of unintuitive. It's famous. It's called the harmonic series. It's pretty. It's pretty unintuitive that this happens, but with Cauchy condensation, if we replace it with this, we're going to soon see that we're basically saying that this sequence, that this series is equivalent to the series 1 plus 1 plus 1 plus 1. And this obviously converges as n goes to infinity. But, why does this work? Well, let's check it out. First of all, this is the main saying. This is the most formal way to say it. So basically, 1/2 of the sum is h equals 1 to infinity of 2 to the power of h, a to the power of h, is less than or equal to our sequence, the sum of our sequences, and which is less than or equal to from h goes to 0 to the power of h, a to h. So the only thing that changes is here there's a 1/2 and h starts from 1, and here h starts from 0. But this is basically what we're saying. And how do we actually prove this? It's such a short and simple proof. We have our sequence here, and let's imagine it goes to infinity. It goes a11, a12, a13, up to infinity. And now let's try to bound our sequence. Let's try to put our sequence into boxes. So here we have a1, here we have a2, a3, here we put 4 of them in a box, and here we put 8 of them in a box, and so on. So we kind of put our sequence into groups. And now we make the size of the groups such as the increase in powers of 2. So this size has a size 1, which is 2 to the power of 0. Here we have 2 terms, so it's 2 to the power of 1, which is 2. Here we have 4 terms, that's 2 to the power of 2. Here we have 8 terms, that's 2 to the power of 3, and so on. We keep on bounding our sequence. Next we're going to have 16 terms, and then 32, and then, it just increases with the powers of 2. So we group our sequence like this, and then we kind of estimate the size of each of the groups. So how do we do this? For example, let's look at this one, 2 to the power of 1. We know that the sum of this is a2 plus a3. But, one thing I forgot to mention. These are the things that you have to take into account. So for this to work, your sequence has to have all positive terms. So either 0 or they have to be positive. And the sequence has to be decreasing. So ak plus 1 is less than or equal to ak, which means each term is smaller than or equal to the next term. So that's kind of the criteria that you need for this to work. So, we have a2 plus a3. And now how do we estimate the upper bound of this? Well, we know that a3 is going to be less than or equal to a2. We know that a3 is less than or equal to a2 because the sequence is decreasing. So how do we get an upper bound of this? Well, we can just say this is less than or equal to a2 plus a2, which, or we can just say 2a2. We know that 2a2 will be bigger than this because obviously a3 is less than a2. And now again, for this over here, how do we estimate the bound of this? Well, we know that a4 plus a5 plus a6 plus a7, we know that will be less than or equal to 4 times a4, because a4 is bigger than all of these. So 4 times a4 will obviously be bigger than adding, a smaller and smaller term every time. And then for the same thing here, we can say that this whole thing is less than or equal to 8 times a8. And now we can see the beautiful thing, like what are these numbers, 4, this is just 2 to the power of 2. It's the size of, it's the size of our little interval. And 8, that's just 2 to the power of 3. So we always, basically, how we can get an upper bound for the sequence is by taking the size of each interval, with 2 to the power of n or 2 to the power of h, and then taking the first term of that interval and multiplying the first term by the size of the interval. And what is the first term of each interval? Well, our first term for the first interval is a1, then we have a2, then we have a4, this is the other first term, then we have a8 is the first term, and these first terms are just, again, this is 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, this is 2 to the power of 3. So basically, to get an upper bound of our sequence, all we have to do, we can say that our sequence from k equals 1 to infinity of ak, we can say that this is less than or equal to our upper bound, which is just the sum from h equals 0. You see, we have to start with 2 to the 0. H equals 0 to infinity of the size of each interval, which is 2 to the power of h. We can say h, k, n, it doesn't matter. But, the size of each interval, as we said here, this is the sizes, times the first term of each interval, which is just a 2 to the power of h. A with the index 2 to the power of h. This is the size of the first interval times the first index, size of the second interval times the first term of the second index. This is how we get our bound. And then to get the lower bound, we do a really similar thing, but now instead we're gonna try to estimate the lower size of each interval, and basically let's just take this one for example. We know that a4 plus a5 plus a6 plus a7, we know that this will be bigger than or equal to 4 times a8, because a8 isn't the next interval, it's the first term of the next interval, and a8 will be smaller than all of these, so the sum of this will obviously be bigger than 4 times the smallest term. So now the same thing we can do here. We're just going to take the sum from h equals 0 to infinity of, again, the size of each interval, that's just 2 to the power of h, times a index 2 to the power of h plus 1. Because here, if we want to bound the size of the fourth interval, we have to take, if we want to bound the size of this interval, which is, the interval with size 4, we got to take the first term of the next interval. So, we got to take a 2h plus 1. And now, we can just simplify this by basically, we can simplify this by taking, we can change 2, we can basically, change this 2 into 1 half, into 1 half times 2 to the power of h minus 1, because, it's just, this is just, h plus 1, because this is just 2, this is just 2h plus 1 over 2 to the power of 1, and then it's just, this minus 1. So, we can change that into this, and then we can see our sequence is, our new sequence, h equals 0 to infinity, we can take the 1 half out because it doesn't have any terms, so we can just take the 1 half out right now. 2 to the power of h plus 1, a index 2 to the power of h plus 1, and so we can see when h is 0, this is 1, when h is 1, this is 2, so we can just start counting from 1, so we can say 1 half the sum h equals 1 to infinity, and instead of the plus 1, we just kind of put the plus 1 into here, we have just 2 to the power of h times a to h plus 1, so we just start counting from 1, and then there's no plus 1 here, so we just start counting from 1, and this is how to get the lower bound, so this will obviously be less than or equal to, and that's how we get this. That's the proof, the Cauchy condensation theorem. That's how you intuitively get it. It's not formal proof, but this is how you construct your thing. And now, why is it so useful? For example, look, let's take the example of the harmonic sum. As I mentioned before, we have the famous an equals 1 over n, and then we have the sum as h as let's say h as, I'll just do n, as n equals 1 to infinity of 1 over n. Well, now we apply the Cauchy condensation the theorem or whatever. So we basically say that n becomes 2 to the power of h, and that's it. So now we can change this thing. We can say this will be asymptotic to the sum as h equals 1 to infinity of 2 to the power of h times 1 over n, but n became 2 to the power of h. So this series will be asymptotic to this series. And what is this? This is just 2 to the power of h over 2 to the power of h. Well, that just equals 1. So this is just the sum as h equals 1 to infinity of 1. So this is just the sum 1 plus 1 plus 1. And this will go to infinity. So this diverges. So then this also diverges. And that's how you prove the divergence of the harmonic series. And, to be exact, this is actually a lower bound. We say here that this 2h, a2h is greater than or equal to ak. So, if this diverges, then we don't know for sure that this diverges. But then, this series is just, you count one less, and you divide it by 2. But, if we have our sequence 1 plus 1 plus 1 plus 1 plus 1, and if we know that this diverges, if we remove 1, and if we divide everything by 2, that's just infinity minus 1 over 2. That's still infinity. So, we can prove it diverges. Okay, and now the last example, just really quickly, we have the sum from h equals 1 to infinity. Okay, maybe not h, I'll do p. P equals 1 to infinity of 1 over np. Now, we can show using Cauchy condensation that this converges if p is greater than 1. So it converges for any p is greater than 1. Well, how do we do this? Again, we change n into 2 to the power of h. So we have the sum from h equals 0 to infinity of 1 over 2 to the power of h to the power of p. So that just equals the sum from h equals 0 to n times 2h, we can't forget this guy, that's, this, the size of each interval. So this is h equals 0 to infinity of, this is 2 to the power of h, this is basically just 2 to the power of h minus hp, or, we can say it's the sum from 2 to the power of h1 minus p, and this, this is basically a geometric series, so if this is negative, then we're gonna have it 1 over 2. So basically, we want this whole thing to be negative for it to converge. It's a classic geometric series, and so this converges if 1 minus p is less than 0, or basically it converges if 1 is less than p, or if p is greater than 1. Because if p is greater than 1, then this series will be 1 over 2 h minus h1 over p. This is a geometric series with r less than 1, so p has to be greater than 1 for this to converge, which is, it's so easy to show. It kind of, maybe, why does, 1 over n, the sum of 1 over n diverges, but the sum of 1 over n to the power of 1 plus 1, that converges, it's like, why, it's such a small difference. Well, we just showed using Cauchy condensation how, using a simple geometric series. That's it. Thank you for watching, and yeah, see you next time.